Okay, so in this video, I'm going to show you how you can easily find a mathematical model that describes your data. So here's the data that I have collected in an experiment. It was a tennis ball rolling down a slope, and I've plotted the data with error bars, and now I'm trying to find a good mathematical model that describes my data accurately. Now, when you look at this, some people might think that, well, those points, they kind of look like they lie on a straight line. So we can try and see if a straight line model actually fits the data. So what we do, I've got my x1 and y1 variables. So in Desmos, in order to do a regression, I use this tilde sign, this wavy line on your keyboard. So y1, I want to express y, say, in terms of a straight line function of x1. Okay, so mx1 plus c. So if I write this down, Desmos is going to give me the best fit straight line for this set of data. And then we can have a look at this and we can see, well, does this mathematical model, this straight line, does it accurately describe all my data? Well, I'm clearly missing some windows of uncertainty, so it's not the best fit. Okay, here the line is missing that window, line is going through that, missing this window again, kind of just missing this window. The line is actually inside this window of uncertainty, okay, just going through the corner of the window, but then it again misses the last point. So this is not a great model. It's missing a couple of the windows of uncertainty. We can also see there's sort of like a slight curve to the data. The trend is a bit curvy, doesn't seem to fit a straight line. Another thing that doesn't make sense is that if I roll the tennis ball a distance of 0 centimeters, it shouldn't take around half a second to roll down the slope. It should go through 0. It should take 0 seconds to roll 0 centimeters. So we're looking for a model that actually goes through the origin as well. So yeah, so even though Desmos gave me, the best fit slope and the best fit y-intercept, and even though r squared is close to 1, so some of you might know that the r squared quantity is a statistical measure for how close the points lie to this line. And the closer it is to 1, the closer the points are to this straight line. 0.97 sounds like it's really close to 1, but looking at the error bars and also knowing that it has to go through 0, this is not a good model. This is not an accurate model. So do we know other mathematical functions, some that perhaps curve a little bit? Well, you might think, or you have definitely heard of quadratics, right? Here's a quadratic going through the origin. But that definitely doesn't fit the data. What about sort of a more general quadratic? So here we have a quadratic that actually goes through all the windows of uncertainty, but again, it misses the origin. And another thing that doesn't make sense with a quadratic is, look at this. If I extrapolate into longer distances, it doesn't make sense that the time suddenly should start getting shorter when the distance gets longer, and it shouldn't take 0 seconds to roll, 290 centimeters. So quadratic model also seems wrong. Well, what other models do we know? And the good thing about Desmos is you can really, write whatever mathematical function that you want. So here's an exponential model, for instance, exponential increase. That doesn't seem to fit. There are lots of different types of exponentials, though. Here's one that looks like this. Again, I can make it go through all my windows of uncertainty. Does that mean it's a good model? No, because we have to look at other aspects of the model. Again, it doesn't make sense that the time should level off, and we also need it to go through the origin. Now, if you know a little bit of physics, then you might know if something has a constant acceleration, then the displacement increases as a quadratic function of time. Now that means that time should actually be a square root function of distance. So let's try and see if time is modeled by a nice square root function, and look at that, bingo, seems like we hit the jackpot. But we kind of knew that it should follow this line if we knew some mechanics, some Newtonian mechanics. So here I have a nice fit. I have a curve, I have a model, mathematical model that goes through all the windows of uncertainty, starts at the origin, and it also just keeps on increasing, right? For ever larger distance, it should take longer to roll down, but it's kind of getting a little bit flatter because the longer it rolls, the faster it's going. So it will cover the same distance in a shorter amount of time as it rolls more and more. So this seems to make a lot of sense, and I have a good mathematical model that is describing my data, and I can read off the parameter that I have here. So this A is 0.176 roughly, and now you can figure out what the units of A are by knowing the units of X, the units of Y, and you can start interpreting that parameter, seeing what kind of information you can extract from that. The R squared quantity very close to 1 because these points do lie very close to this square root function. So that's a good model. Okay, so that's how you do that. And again, to remind you, remember, don't just screenshot, export the image nicely. And you can also, remember, change the color of these lines. So you get a really nice graph that you can post into your lab report. Okay,